Today we're doing collision mechanics. Next week you have a test. Let's do a quick poll here on the test. The past two tests, at popular request, we made the homework due Thursday and the test did not cover the homework. The alternative is to have the homework due Tuesday so that between now and Tuesday you can do homework and study for the test as one single activity. If we make it due Thursday, you can study for the test, which will only cover through the homework which you're handing in today, but then you'll still have to do the homework after that. Presumably you only have 2 days to do it unless you have extra time to both study for the test and do the homework over the weekend. Is the question clear? Okay, we're going to take a vote. A is going to be that you would like to have the homework due Tuesday and have it covered on the test. And B is going to be that you want the homework due Thursday and you want it not covered on the test. Is the voting clear? But the right answer is A. You only get 4 points. Just kidding. Okay, so we'll have the homework due Thursday. I would say these people are procrastinating masochists, and these people are people who are planning ahead and take good care of themselves. But it's your choice. Okay, so today I want to do a new topic, which is what we call collisions. On the syllabus, it's what we were supposed to do last time, so we're precisely one lecture behind. My goal is to do just one example, a somewhat long example, and to introduce the topic. So the basic idea in collisions is sometimes you have big forces acting for a short time. So when does this happen is when things bump into each other. Things bump into each other. They are very stiff. You think of them as rigid. They have an interaction which is very short in time, yet the velocity changes, which means the momentum changes, which means there is some net impulse. Impulse is the integral of force with respect to time, yet the thing happens in a very short period of time. So to keep the idea clear, in an example, look at just what we had as the particle example, and we look at some force acting like this. And let's look at a force profile which looks like this, force as a function of time. And we can look at a profile which goes up and comes down like this. And we're not saying that this is exactly the shape, but this is the idea that we'd like to get across, where we have a delta t here, and we have an F0 here, and we want to know what is the effect of this force on this particle. So, as an example, let's just say this thing starts from rest. The particle starts from rest. And let's just call this time, just for convenience, let's just call this time 0 and say what happens in this collision. What happens between 0 and t, and this is less than what I'll call delta t. What happens in this time interval? So what happens is we have the equation F is equal to ma. We can rewrite this as F is equal to m dv dt. And now we have this F is equal to a constant, F0. She's just learning how to erase blackboard. She's not very good at it yet. So I told her to use a wet sponge, but I didn't tell her she had to dry it afterwards. So. These professors are no good as janitors, as a rule. Okay, I think I'll wait for that to dry and give a motivational example. So we're just going to stop that and switch to a motivational example. So this is from my lab, and this is a robot. This is going sometime back in time. This is like 12, 13 years ago. We're still working on robots like this, but what's nice about this one is that it's clearly two-dimensional, and it's just a machine. I haven't showed this video to you before, have I? Okay, so this is a machine that's made out of sticks and hinges. So it's very much in the area of what you want to understand in this class. Play full screen somehow or other. View, full, present movie, play. Okay, so this is sticks and hinges, and it's walking down a ramp. So this is a ramp. It's still in my lab upstairs. It's a little higher at this end than it is at this end. And this thing is got no computers and no motors on it, so it's just sticks and hinges, all the time obeying the equations which we use in this class. Now, it's a little more complicated than the problems we've done in this class. When you're done with this class, if you were very good, you could patiently write the equations for this. It's tedious, and it would take you about a month probably, but you have all the skills. What's going on here is in this configuration, say, this leg, which has a thigh and a shank. By the way, this is one piece of metal that goes all the way across here like this. And this is then the shanks. These two are not connected, but they move together. Then the middle leg here is a thigh and a shank. So conceptually, this is a two-dimensional machine. So it fits in the analysis that you learn in this class. And in this configuration, you have an inverted pendulum. Well, it's not quite an inverted pendulum. It's rolling. Actually, these feet are round. So this exactly fits in the rolling mechanics that we've done. It's just that instead of being a round object, it's a round object with a center of mass and moment of inertia are funny because it's connected to this long leg. But this rolling of something like this inverted pendulum you can handle. But it's actually a double pendulum because this is hinged from it, and it's a triple pendulum. So it swings along like this, obeying equations F equals ma, m equals I alpha for all the parts. And then it has this collision with the ground. Now what happens here is there's a sudden discontinuity in the motion, and there's very large forces. So to write the equations for this whole walking motion, we use smooth differential equations, integrate them with actually literally ODE 4-5. And then we get to this point where the foot hits the ground, and then we have a jump condition, just like you had for your particle mechanics. Remember, you had these particles banging into each other, and you have a jump in velocity and no change in configuration. And you see from just before here to just after here, the robot, from here to here, the robot configuration, well, changes a teensy bit because a 30th of a second passes by. But basically, there's no change in the configuration. Yet there is a change in the velocity. This foot was going down before the collision, then it's still afterwards. The back foot was rotating about the back foot contact point before that front collision, and after the collision it's lifting up. So what happens is if you had a soundtrack here, you'd hear this go bang. That corresponds to a big force, much bigger than gravity force, and a discontinuity in the velocity and no discontinuity in the positions. We have what's called a jump, which doesn't mean jumping in the air, but a sudden change. In math, when a function has a jump, it means a discontinuity in the function. We have a jump in the velocities, but not in the positions. And then we start new differential equations for this next phase of the motion. Okay, I'm going to stop this robot. But this is when I said at the beginning of the semester, this stuff in this class is not useful, what I meant by that is the majority of engineers out there in the world are not using the differential equations in this class, unlike the stuff in TAM 2020, which there's thousands and hundreds of thousands and millions of people doing it. But if you want to study things like this, you have to master the material in this course. So it's 100% useful if you want to, for example, go into robotics. Any questions about this example? Yes? Can it walk backwards? Yeah. No, it would not walk backwards. You know why? There's a second collision which I didn't describe to you just now, which is, here, I'll get it closer to you so you can see it, which is we have what we call knee strike, which is when the leg gets straight. And that's not a reversible motion. So right here, bang, the leg gets straight, energy is lost, and going backwards, we'd have to have an explosion at that point. Now, as far as the other collision goes, this one, there's a bang here. To have it walk backwards, we need a backwards bang. We need an explosion. So in this direction, energy is lost in the collision. In the other direction, we need an explosion. So the equations of motion are all satisfied forwards and backwards, but we need to replace plastic collisions with explosions to make it actually work backwards. And then that says nothing about the stability. This happens to be stable, which means if you give it small perturbations, it recovers from them, which is kind of a remarkable and amazing thing about this machine, which cost me, in a negative way, perhaps about 10 years of my life. Because this stability is deceptive. It makes you think it's important maybe for human walking, and I now think it is not. It's a lucky accident that makes it so we can make this video, but it's not really useful for understanding how people work. Okay, any other questions? Okay, so this is an example of why you'd want to understand these collisions, is to understand that systems like this, but machine parts, more mundane machine parts also have these collisions. You need to understand that perhaps in your 225 machines you also have collisions that you could conceivably try to understand. Okay, so now we want to understand these collision mechanics. We have this differential equation. We can integrate both sides with respect to t. We can integrate from 0 up to delta t. On the right-hand side, we get the integral from 0 up to delta t of dv dt dt. This is some function, but by the fundamental theorem of calculus, this just turns into m times delta v, and this turns into what I'll call p, and this defines what's called impulse. So the word impulse, on the one hand, means a sudden large force, but more generally in mechanics, it just means the net momentum transfer. Now, what happened here is that all that shows up in this thing is F0 times delta t, which is the area under the force versus time curve. Which is this area here. So what we call the impulse is this thing, which is this integral of f dt. It's the area under that curve. Now, what happens to the change in the position in this time? Well, in this case, if we just take in this example, and this is just a for instance, so that we can do the calculation, which is a constant force, but the same idea holds even if the force is not constant. F is constant. And why do I add this when I already assumed it? Is that this part actually is more general than assuming the force is constant. Then what we have when the force is constant is that the velocity is equal to v0 plus at, but velocity at time equals 0 was 0, plus at, that was at f0 over m times t. And so the velocity evaluated at delta t, this just is the velocity at all times, so it's just f0 over m t. Now if we want to figure out what x is, x at time delta t is equal to x0 plus the integral from 0 up to delta t of v dt, but v we figured out is f0 over mt, so we have x0 plus the integral from 0 to delta t. Now I don't need to use dummy subscripts here because my upper limit of integration has a different symbol than my integration variable. So I have f0 over mt dt. x0 we set as 0. Let's start this thing like this. And so we have delta x during the collision is the integral of this thing, which is f0 over m delta t squared over 2. Now another way to write this is as p times delta t over m, like so. And the key idea here is that the limit as delta t goes to 0, but p is still fixed, is 0. So there's, if the time is short, if the time duration is short, that implies that the change in position is negligible. And the same thing happens for angular impulses. So this is what the idea is collisions. Something, a big force in a short time where there's a change in velocity and no change in position. How do we do the mechanics with free body diagrams? We use what's called a collisional free body diagram. And in a collisional free body diagram, you neglect non-collisional forces. And I'll show you that in an example, which I'm going to do for the rest of the class. But the idea is that some force like gravity is a finite force, and if over a short amount of time, the change in velocity it causes is the force times time, as the time gets shorter and shorter, the net effect of the gravity force is smaller and smaller. So we assume that in that teeny interval of time, when there's a rapid change in velocities due to the collisional force, there's a negligible change in velocities due to the gravity force. So we draw a collisional free body diagram where we neglect non-collisional forces and we just show the collisional impulses. And you have to be clear when you're drawing a collisional free body diagram, then that's what you're doing, that you're showing impulses. That's FDTs and not forces. So let me do an example. It's similar enough to your homework conceptually that it should help you with your homework. So here we have a block. Let's assume it's a square block. And what I'd like to do is drop it. And when I drop it, I'm going to drop it from a nearly vertical position. And then it's going to fall. Then there's going to be a very big force. And then maybe it bounces up a little bit, or maybe it doesn't. Okay, so it falls, and it bounces a little bit. Okay, so I'd now like to analyze this situation. And the way I'm going to do this is I have to make a model. A model means I'm going to make assumptions about the nature of the objects, so I know what I'm putting into the mechanics equations, and the nature of the interactions. So to keep it simple, I'm going to assume this is a rigid object. I'm going to assume it's square in cross-section. I'm going to assume it has a uniform mass density. I'm going to assume that there's enough friction on this corner so that this is a hinge and it rolls without sliding. And then I'm going to assume that there's a collision here. And to make the calculation simple, I'm going to assume that this is what's called a plastic sticking collision. So that means I'm going to assume that this sticks. This point does not bounce up. It might rock up like this, but this point is going to stick and it's not going to slide. Now if you watch the experiment, you'll see that this does slide a little bit. And I could do that calculation too, but that would be a little bit harder calculation. And just to keep things simple, I'm going to assume this sticks. So we can assume, for example, that I've got some other piece of rubber here that keeps this from sliding. Maybe now it won't slide if I do this just right. No such luck. I need to put a ruler here or something to keep this from sliding when it hits. That kind of did it. So it falls and it rocks up a little bit. The question is, can we calculate how high it rocks with those assumptions or not? Okay. Any questions about the experiment? Most of the hard part of a problem like this is the setup before we get to the calculations. If I spent the whole lecture on the setup, you would be mad at me for not showing you the algebra. On the other hand, if I showed you the algebra, you would, on exams, you would get confused, because most of the times problems like this, when people go wrong, they go wrong at the setup, not in the algebra. As I think those of you who had trouble on the exam so far know, even though all the time is spent on the algebra, all the credit, almost all of it, is in the setup. Once you know how to do the algebra, Actually doing it is not the hard part of the problem. So we want to get the setup right for this problem. I'm going to start setting it up on this middle board. Maybe I'll state the problem over here on this board and then start working it on that side board. Well, that one doesn't count anyway. Okay, so here's an example. A block falls, hits at the corner, then tips up, and then the question is how far? What's the joke?
Cornell.
I've told you I'm senile. And maybe there's something deeper about that. Somebody in a lecture yesterday talked about corner cases in trying to figure out air traffic control systems. He said there's always the corner cases. And by corner cases, he meant exceptional cases. So maybe that's what I meant. Okay. So how does this situation go? We're going to have a starting situation. And in the starting situation, the block is going to look like this. And it's going to be tipped a teeny, teeny, teeny angle. And it's going to be such a teeny angle that we're actually going to neglect it in our calculation. Then it's going to get to this other state where it's having this collision. So here's the start. And here's the collision. And then it's going to get to this end state where it's tipped up maybe just a teeny bit. We don't know how much. That's our goal, is to figure out this end state, which is how high it tips up before it falls down again. And this will have this angle here, which we'll call theta sub end. And our goal is to find out theta sub end equals what? Now what happens in between is somewhere in here there's a period of falling when this cube is at a some kind of falling configuration, and it's falling some angle here, and I'm going to call this angle theta. And because of my dislike of negative numbers, actually I've been advertising to you that you should trust negative numbers, but I have a dislike of negative numbers. Hey, you guys in the back, the last row with people in it, move forward, please. 3 of you back there. Last 4 rows on the middle, last 5 rows on the side. There's seats up here, please. Yes. That's you, yes. Thank you. I really feel like a jerk when I do that, but if you don't hold the line, things fall apart. Okay. This is then in this falling configuration, and I'm going to take this angle here as positive, which means I better be careful if I'm going to use angular velocity formulas, because it's nice to take angular velocity to be counterclockwise if I want to use cross products. So implicitly here, I'm going to be having that omega is minus theta dot k. So I've got to look out for that in my sign convention. Then after a while, it's tipping up again. And it's in this tipping up process. So this is tipping up. And this is going to be some theta of t as it's on its way up. And then there's 2 more pictures which are nice to draw, which is just before the collision, when the configuration is basically the same as the configuration during the collision, and just after the collision. And just after the collision, the configuration is still basically the same. It's just tipped by some teeny angle, which is not going to show. So here's just before and just after the collision. Now, when are we going to be doing mechanics? We're going to be doing mechanics for this collision. We're going to be doing mechanics for this falling, and we're going to be doing mechanics for this tipping up. So in this configuration, we're interested in having a free body diagram. And what's the free body diagram going to look like? Here we have an mg, and here we have some normal force and some friction force, which we don't know how big it is. And we're assuming that this block doesn't slide. So this is going to be acting like a hinge in our approximation. Here we have the situation just before and just after, and we're thinking about this in the context of the collision calculation. And in the collision calculation, we have some big impulse here, say P sub n, and we have also an impulse in this direction, say P sub f. And this might turn out to be a negative number if we calculate it, but that's not going to matter. So this is our collisional free body diagram. Then we have just after the collision. This situation we use a minus sign, meaning it's just before collision. This one we use a plus sign, meaning it's just after the collision. And as this thing is going back up again, and there's an n here, and an f, and an mg, and then eventually we get to this top state. Now what are we going to do for calculations is in this phase we have this point here, and let's just call this point C. In this phase we're going to use angular momentum balance about C. That would be a good equation to use. Or we could use energy conservation, and that's going to be better for our purposes. In this, and that applies in this phase here. In this phase, we're going to use a collisional calculation. And here's point C over here, and here's now point D, collision calculation. And the thing we can use here is angular momentum balance with respect to point D. And then in this phase here, we have point D. We could use angular momentum balance with respect to D, would be a good one, or energy conservation. And then that takes us to our final state here. So if we label these states, let's call this state 1, 2, 3, 4, 5, 6, 7, then that gives us a way to think about organizing the calculation. What do we imagine we're given over here? We imagine we're given, say, the mass, the side of the block, the gravity constant. Do we need anything else? If we assume this is a uniform block, then that implies that the moment of inertia about the center of mass is equal to A, B, C, D, or E. Okay, you figure it out, talk to your friends, and then I'll put up some choices up here. And I'm not going to just put the right answer and ask for the honor system because I know that you guys lie. So I'm going to give you some actual choices. Let's see, no calculators, no books, no notes. Yes? G is the center of this square. So G is sitting here. I've got C, I've got D, I've got D, I've got G, C, D, G, G, C, D. Okay, you have 5 seconds to vote. 1, 2, 3, 4, 5. Is this social dynamics or mechanical dynamics? I do not know. Stop. Andy says the right answer is A, B, C. Oops. A, B, C. I like that one. Okay. Now, those of you who actually did the whole calculation right now, just raise your hand. Okay, so some of you did. Those of you who did not, make sure you know how to do that calculation. Yes?
Aren't the units of I a distance to the fourth?
The units of I are distance to the fourth times density. And density is mass divided by distance squared. The units of I in TAM 202 were distance to the fourth. That was the area moment of inertia. In this class, the moment of inertia is the mass moment of inertia. It's the integral of r squared dm. In TAM 2020, so in this class, Ig is equal to the integral of r squared with respect to g dm. This is 2030. In 2020, we had Ig was the integral of r squared with respect to g dA. That has dimensions length to the fourth. This has dimensions length squared times mass. Mass, dm itself, has dimensions of dA times density, but density has dimensions of mass per unit area. So this comes out distance squared times mass. Does that answer your question? Are you happy with that? Okay, any other questions? Any questions about anything on the blackboard so far? Yes? On diagram 4, we do not include the force of gravity because our assumption is that time 4, that's just after time 3 when it looked like this, and it's just before time 5 when it looked like that, there is a big loud sound, and that's associated with the force which is so big that gravity is negligible compared to it. And it's acting over such a short time that in that time interval, when the velocity changes, the change in velocity due to the gravity force is negligible. Now, how can you tell that that force is big? Well, I can put my finger under here, and I'm carrying the gravity force, and it doesn't hurt. But if I put my finger under here and go like this, ow, it hurts. Right, and I just nicked it. If I would have put it right under, then it wasn't that bad. But it hurts a lot more than this hurts, right? So that force is a big one, that collisional one. If you want to know if it's a collisional force, imagine yourself in the middle, and then think if you don't want to be there, that might be a collisional force. Okay. So this system, for all time, has 1 degree of freedom. So at every instant in time, we can characterize the velocity with a single number. So in terms of organizing the calculation, if we look at phase 2, we have this choice. If we don't care about these things, we get rid of the things we don't know about, don't care about, these reaction forces. We could use angular momentum balance, or we could use energy conservation. What are the pros and cons of these two? If we use angular momentum balance, we'll get a differential equation. What will it be? It will be the pendulum equation. It will be the inverted pendulum equation. That just has to do with whether the plus or minus sine of theta. That's a nonlinear differential equation. If we want to know the state of the thing when it gets to here, from solving that differential equation, we don't know how to solve it except for with, I forget, what are they called? Elliptic integrals or something like that. Or on the computer. So we could do that as a computer solution, getting from here to here. But between these two states, we also have conservation of energy. And that tells us the final state in terms of the initial state. So if we want to do this without the computer, then conservation of energy is the right thing to use to get from here to here. Any questions about that? Okay, so for phase 2, conservation of energy will give us what I'll call omega minus, the angular velocity just before it hits. Then at phase, this one, phase 4, if we are given omega minus, that's given the angular velocity just before the collision. If we use angular momentum balance with respect to point D, then those collision impulses don't show up, and that will tell us omega plus if we do this calculation carefully. And then when we get over to phase 5, not phase 5, phase 6, phase 6, we're going to be given at the beginning of that phase what we'll call omega plus, and then we'll use conservation of energy again. And that will give us theta, what did I call it? Theta sub E. And this is our goal. And that means we have an answer. So now all that's left is actually to do the details of these calculations. So it's just a matter of, can we use conservation of energy? Can we use conservation of angular momentum? Can we use conservation of energy? One calculation, second calculation, third calculation. Everything look clear? Anybody have any confusion? Okay, once you've organized the problem like this, it's really just grinding things out, and there's no step in this calculation which I think any of you should have trouble with, but it's just doing a calculation that you haven't perhaps done before. So let's look at phase 2 and actually do the calculations. So what we have is E total at phase 1 is equal to E total at phase 1, 2, 3, just before the collision. E total 3. Okay, now we have to figure out what is the energy here. Well, here is mg d over 2. That's the length of a side, but it's tipped up in this funny 45-degree way. So the height of this thing is d times the square root of 2 over 2. And we're going to use as our datum for potential energy is the ground. So we'll measure potential energy relative to the ground. So we're going to use this as our h for potential energy. So sometimes people use this symbol here to mean the datum, the reference point for measuring potential energy. Now afterwards we have this kinetic energy to worry about. We could use the freshman physics formula of I omega squared, where we measure I relative to the corner. I do not advertise that because that does not work for all problems. So to have a more general result, we put over here that we have our final potential energy, which is mg d over 2. It's the center of mass is only up a height d over 2 at this point. So this is EP1, and this is EP3. And then we have plus the kinetic energy at just before this thing hits. What is the kinetic energy? It's the sum of two terms, 1/2 mv minus, I'll call it squared, plus 1/2 ig omega minus squared. So this whole thing is the kinetic energy at stage 3, which has two parts, a rotational part and a translational part. But just before the collision, point G, this is the velocity of point G, is rotating about point C. It's going in circles about point C, so its speed is omega r. So this V minus is equal to omega minus times d times the square root of 2 over 2. So that means we have this whole thing as ek as a function of omega minus. Okay, so if we do all this arithmetic, this is going to tell us what omega minus is, and it's equal to something, and I'll just leave the algebra to you because we don't have enough time. Any questions about phase 2? Think about anything on the blackboard. Anybody feel insecure about the formula which I did not write down for omega minus? If we given numbers for the mass, the g, the d, and so on, we can calculate the omega minus as a number. Okay, I asked any questions, but I didn't look up. Yes? Where did this come from? Because this block is tipped up like this, and we're looking at the height of the center of mass G here, and this height here of this center of mass is equal to d times the square root of 2 over 2. So height, does that answer your question? Any other questions? Okay, now we need to worry about phase 4. Did I count that right? Phase 1, 2, 3, 4. And we'd like to go from omega minus to omega plus. And this is a tricky one. I mean, it's not that tricky, but it's maybe somewhat new to you. So in phase 4, we're going to use angular momentum balance about point D. And what this is going to say is that the angular momentum relative to point D just before the collision is equal to angular momentum relative to point D just after the collision. Because all this happened is an impulse at point D, which has no torque, and therefore there's no change in angular momentum relative to point D. But now we need to calculate what these things are. So this is the position of point G relative to point D crossed with the mass times the velocity of point G before the collision plus Ig omega before the collision K. And this thing is exactly the same formula, the position of G with respect to D crossed with mv of G after the collision plus Ig omega after the collision K. Okay, copy that formula down, stare at it for a second, and then ask me a question about it. Okay, before the collision, this thing has some omega. By our sign convention, it's going to be a negative number. After the collision, it has some omega. By our sign convention, if this bounces up at all, it will be a negative number. The motion before the collision is a rotation about this point. The motion after the collision is a rotation about this point. But we still have angular momentum balance conservation about this point. So before the collision, when we calculate angular momentum balance about this point, we have this velocity to deal with, which is orthogonal to this line, and we have this angular momentum. After the collision, we have this velocity to deal with and this angular momentum. Before the collision, because this happens to be a square, this velocity is directed right at that corner. So the contribution of that first term in that formula to the angular momentum is what? Let me say that in other words. Very good. Why is that? Because this velocity is along the line. This velocity is orthogonal to this line. And orthogonal to this line is straight down towards that corner. And we're taking the cross product of r cross mv. Those two vectors are parallel. It makes no contribution. Okay. So we have to, if we're just going to grind this out, we've got to put these things down as vectors. If we're going to put these things down as vectors, we've got to say what our directions are here. Here's I and j. So for r g with respect to d, we're going to have minus d over 2 times I plus j. That's what this thing is. And then for this vg minus, what is that? It's rotating about point C, not about point D. So this is omega minus k crossed with the position of point G with respect to point C, not point D, because even though we're taking angular momentum balance with respect to point D, before the collision, it's rotating about point C. So this is an important thing to distinguish. And this rg with respect to C is d over 2 times I plus j with a plus sign. So you can't just use simple pattern recognition and say, here's a d, there's a c. That's wrong. That should be a c, and this should be a d. Then over here, we know what this thing is. We've calculated that. And then there's v plus. Now this rotating about point d. So v plus is equal to the position of g with respect to d, omega plus k crossed with the position of g with respect to d. And what is the position of g with respect to d? That's this thing we already worked out over here. That's minus I plus j. D over 2 minus I plus j. Okay, now if somebody had a question? Yes? Here? Point what? You're just wondering how I spelled the letter D? Is that your question? Are you happy now? Okay. So now, this whole thing is an expression that involves omega plus and known things. And from this, we get omega plus is equal to dot, dot, dot. With algebra, you can do. And then finally, we get to phase 5. Phase 6. And we use energy conservation again. And we have to be careful about the geometry, but this will then tell us that from omega plus, we get theta end. And this calculation is just like the first calculation, but with a little more careful geometry, because you don't know what theta end is, so you have to calculate that final potential energy. Okay, any questions about this example? Anybody feel like they could not do it themselves? Is there a question you could ask that would make it so you could? Too fast today? Too slow? Just right? So perfect you can't stand it? Okay, see you Thursday.